Alright, I just double checked and make sure that the stream is on. It took a little bit of time to get to it though, so that's a little strange. Usually it doesn't take close to a minute before anything shows up on that side. And the lag time doesn't seem to be too bad. Maybe it's just, the initial spooling time that seems to be kind of bad. Alright, so we got about right. Well, as long as I don't, kind of frail around and, knock off my cable, we should be okay. So what we'll do today is we're going to take a look at the lab on Tuesday. And I'm going to do the lab, from the beginning. Unfortunately, there's no way for me to reset what I know about the subject matter so that I can truly, actually do everything from scratch. So, but I'll do my best, okay? I'll try my best to explain, how things connect. Yeah, so that's kind of important. And then the second one, you probably have heard me talking about this many times already. And people who come, show up early probably are not. They're aware of this already. Is you have to kind of spend about 5 1/3 of an hour each week to kind of study, review the material, and so on, for any type of 3-unit class. So when I say 3-unit class, I'm referring to the lecture units. So the lab unit does not require any extra time, but the lecture unit does. So it's 5 hours and 1/3 of an hour. It's 5 and 1/3 of an hour each week. Yes, I know it's kind of intense, but that's kind of what we need in order to kind of get the background or the foundation material sink in, as we stack more things on top of those earlier concepts. All right, we got about 10 more seconds, and hopefully people are showing up. I got about 40 people. Okay, I got about 40 playbacks. I'm not really sure how they count. Let me click on the question mark. How they count concurrent viewers versus playbacks. Alright, so concurrent players, according to YouTube, is the number of viewers connected to this stream at the most recently available time. And then playback, which is now at 43, is the total number of times the video has been played. Oh, okay, so if the same person kind of, checks in, check out, check in, check out, and check in, check out, that will increase the playback count, but not necessarily the concurrent viewer count. I'm guessing that's the case. Anyway, we're going to get the class started here. And I will do the preview mode, so that way, I am actually looking at the questions the same way that you do. In fact, I can even turn on student view. And of course, I cannot remember the passcode, but I think it's 3x3 part 1. There we go. Alright, so will it let me actually do it? And the answer is nope, it does not let me do it because I'm a student. Alright, so I cannot do it as a student because as a student, it's already past due. Alright, no biggie, no biggie. So all I need to do is to go back and, well, that's just the submission. Alright, so here we go. We just go through this one by one, step by step. Alright. So as you guys have questions, please do not hesitate to ask, because if you have any conceptual questions, it's really kind of important to get those things addressed as early as possible. Alright. Yep, good evening. Alright, so what I'll do is I'm going to start up LogicSim. and then I'll just follow my own instructions and kind of get everything done. So the first thing is I'm going to have to recreate the circuit like the way it is now. So we'll go ahead and create the circuit. One little tip that I have mentioned already in the past is if you want to get your input pins and output pin, it's best to get it from here instead of from wiring down here. There's a difference. These ones already come with 3-state automatically turned off or by default turned off, and that's how we want it to stay. And we want 3 bits. Okay, so we want 3 data bits because we are trying to create a 3-bit by 3-bit adder. So the input is going to have 3 bits. So I'm going to call this one X, and then I'll use Control D to duplicate it, and then call the next one Y. Okay, so drag around and then call this one Y. Y also has 3 bits because we are creating a 3-bit by 3-bit adder. And then I'll duplicate it one more time, and then this time it is going to be my K0, and K0 is a single bit, so you have to change the number of bits or the bit width to 1, and then we change the name to K0. Alright, so at this point, okay, there are still a few things that I would like to point out. The first one is the label of a pin is cosmetic. Okay, that's all it does is to show you, oh, this pin is also called K0. This pin is also called X. It's strictly just for decoration purposes. On the other hand, when you use a tunnel, it is not the same. So when we pull a tunnel like so, you will notice that a tunnel has its own phasing. Now, the phasing is significant because where we make the connection, see how this dot here, by the time I move my mouse pointer here, it turns into a larger circle. That's telling you that this is the pin, okay? This is the port. This is where you actually make the connection. I think the way I saw some of the circuit diagrams, some people have forgotten that you have to carefully find out what is the actual connection point of a component. So that is really kind of important, because if you do not connect to exactly that point, then it is not connected. Even if it looks connected, it may not be actually connected. So I'm just making 3 of these things, because one for each input pin, because I'm just trying to recreate the diagram in the quiz. So I forgot to change the width, and so it complains. Alright. The question is the label the same as adding text manually next to an item? Not exactly the same, because if you just add text next to an item, the text does not move with the item. In this case, if you move the pin, the text does move with the pin. So it's a little bit better than that. Alright, so first thing first, there were a few people who were asking questions about what do we do at this point now that we got some orange colored wires. So the answer to that question is, well, we have to adjust the width of the components so they are the same. So one thing you can do is to click on a particular component and just look through the properties of that component, and we can see that this one has 1 data bit, and then this one has 3 data bits. So that's why they do not agree, and that's why we cannot draw a wire across these 2 items. So they must all have 3 bits. Okay, so we gotta change all of these to 3 bits, and then the last one has 1 bit, so the default is fine. Next thing is to label these things. So as you label the tunnels, you have to be careful because it is case sensitive. In the questions, I did not specify whether you have to use uppercase or lowercase. So it's up to you, but you just have to be self-consistent. Let me switch back to the notes here, and these appear to be in uppercase. So I'm going to use uppercase here. So uppercase X. And someone there was one person who got into the problem of using different cases, and if you use different cases, they would be considered distinct, and as a result, all the tunnels that seemingly are of the same thing, they are not really of the same thing anymore. Alright, so we got a text in. I also added text on top of the tunnel and it connected it automatically. I'm not sure that would do it. I mean, what do you mean by connecting? Are you connecting the wire? Are you referring to the node itself getting connected, or are you referring to the text being quote unquote connected with the tunnel so they move together? That it wasn't clear. Does K1, K2, and K3 find out the carry from one 3-digit binary number to the other? Okay, that's kind of down the line. Okay, so I'm not going to address that question just yet because I'm working on this sequentially just the same way as you did. So by the time we get there, please ask that question. Try it real quick. Use the text tool on top of the tunnel. No, it connected the text to the label. Okay, so let me try it real quick here. Alright, so I'm just gonna do that, and then we'll move. Okay, oh, okay, that is kind of cool. I did not know that the text automatically attaches to the closest object. Oh, it maybe not. It does not actually do that. So, no, okay, no, it does not connect to the component. Alright, maybe I misunderstood the instructions in the text channel. Alright. Maybe. I'm not sure. I'm not sure. But we are going to continue because I gotta kind of watch the time because I really want to get you guys this file so that even people who did not finish on Tuesday, they will still have this file as a starting point for today's lab. Alright, so let me just go ahead and answer these questions. What is the purpose of the label of a tunnel? There may be multiple correct answers. Select all correct answers. It identifies connectivity between individual tunnel instances, and as tunnel instances of the same name are logically connected. Yep. It is displayed as a visual label. Yes, it does. A tunnel with a label automatically connects to components other than tunnels of the same name. Not true. And then the last one is the label is only used when a circuit is printed. That is also not true. So these two are the correct answers. Alright, so moving on. So the second part, or question number 2, is just giving you the template of something, and then we have to figure out how to actually interconnect between these things in this particular picture. So that's still a part of the circuit that we are creating right now. Let me just decrease the zoom level by 1 step just so that I have more space to work with. Alright, so we are going to create a bunch of tunnels, and I'm just going to be lazy by reusing things that we already have. So here's a Control D. It duplicates everything that is selected, and now I can move the entire selection down here, and obviously they're all pointing into the wrong direction, and well, that's easily fixed because even if you have multiple items selected, you can see that the common property will still be changeable by using the selection pane. So in this case, I do not want these to face west. I want everything to face east, so they point in this direction. And I also need 3 more on the other side, even though the labels would need to be changed for some of these. But I'm just trying to use at least as little time as possible to do this. So I'm just replicating them first. Oh, I forgot to change the facing first. There we go. Let's change the facing to west. And then we have to change the name or the label of the first 2. So X needs to be changed to, oh, actually all 3 need to be changed. So one is P, one is G, and one is Q. Okay, so whatever order you want to use is not really that important. So I'm just going to preserve P, G, and Q. So as I'm working on this, okay, it is important for you guys to understand that all of these terms were defined by the time the lab was assigned. And this is also why in class I quite I reminded you guys multiple times to kind of write down the definitions, put the definitions at one place because you need to refer to those. Okay. I also remember distinctly that I pointed out the definitions of P and G because they were kind of tucked away in a paragraph that does not seem to have any significance. So I definitely just specifically pointed out the definitions of G and P in the lecture. So when I do something like that, okay, it might be a good idea for you guys to write down some notes. So there you go. Alright, so I'm just going to the text channel and see what is there. Once we got into the subscript, I got tripped up. The subscripts. Okay, so we just wait until we get there, right? Okay. Alright, so now we are done with wiring. We just have to get to the gates. And the three gates that we have placed here, the first one is exclusive OR, and then we have regular OR, and then we have regular AND. So I'm going to do the same thing. Even though the instructions said to kind of move those things around, so I'm going to move those things around so that they actually align with whatever tunnel on the right hand side corresponds to the gate. So this is our first one, and here is our second one. There we go. And then our third one is an AND gate. So there we go. Now, if you change it on this side before you place the component on the other side, it's going to change the default. So from now on, whenever I try to pull an AND gate, this is the default AND gate that I'm going to pull, because it's kind of handy, to do this later on. Just because we usually do not want a wide gate, we want a narrow gate. Alright, so at this point, what we want to do is to find the definitions of all of these terms. Okay, the P terms, the G terms, and the Q terms. I'm not going to go back to my notes to show you exactly where to find them, but all I can say is they are all in the notes. Okay, there's one specific one that I want to point out because that one is a little bit tucked away, but it is not like missing entirely. So that would be the exclusive OR. When we define R for binary addition, that portion does. Oh, actually, this is the wrong module. This is for binary subtraction. Okay, fine. I'm just gonna change the module number to 3. There we go. All right. So there, when we talk about the R function, so R of something. Oh, there we go. I'm using the search function, in a browser. That can be quite handy, but I'm not. There we go. All right. So how does the computer do this using transistors? Yes, I know there's a lot of text here, but it's kind of what you need to do to kind of read through the entire thing. So the way it mentioned that this can be done with an exclusive OR is right here. The other one is a little harder, referring to the R function instead of the C function, which is really just conjunction. In two cases, when x and y are different, it equals to 1 in two cases when x and y are different. Technically, there is a Boolean operator called exclusive OR that does exactly this. So this is where it says, yep, you can use an exclusive OR gate to implement the R function. And then combined with Q of I is R of xi, yi. That is how we get the circuit done. So are we good here? Does everybody understand how I got to, mapping the exclusive OR gate to Q and understand that it is X exclusive or Y that produces the Q bits? Alright, cool. There's a thumbs up. I was actually expecting someone to make a snarky remark and go like, That is not obvious. Well, I have to admit it. It really is not obvious. But if people need everything to be obvious in order to get it to work, to actually understand the content, um, I'm going to say computer science is going to be a continuing uphill battle because things definitely are not going to be obvious. Most things in computer science are very abstract. And then we got some question here. Yes, it is not obvious, Mohammed. Very good. Well, it is obvious that it is not obvious. All right. So Brian said, so in exclusive OR, it is either X and not Y or X not X and Y. It is just a regular OR. There's no either. It's just by the very nature of X and not Y versus not X and Y that only up to one of them can be true. But the actual definition is just a regular OR. Alright, so I'm going to wire up the thing. Your X is going to have to go into each one of these gates. So we got one up. Okay, forgot to change the bit width again. So I'm going to be lazy. You select all of them and change the bit width of all the gates at the same time. So the idea of using, oh, that doesn't seem to work. Alright, so maybe I need to rewire again. Alright, so let's try that one more time. Data bits, go to 3. There we go. Okay, must not have selected everything. Alright. So we go here, and then we get one to go over here. And then Y is going to be doing be connected to the other input pin of all of the gates. So for each gate, we now need to connect Y to the other input pin, like so, and oops, like so. Alright, there we go. Okay, so there we go. Yeah, exclusive OR is actually a bitwise operator in C++, but I just don't think a lot of classes cover that one. So now we just have to make connections from the output of each gate to the tunnels of the name of the corresponding name, like so. So there we go. Let's go back to the quiz and see what else we have to answer. Okay, so there we go, and the quiz is right here. All right. So this is my favorite. Okay, it actually took me a lot of work to make this, so that it is, different people would actually get different values for X and Y. As it turns out, in this case, both X and Y are 110. K0 is not used, so it can be anything. So this is a pretty good clue, to when you're drawing the diagram up here. This is a pretty good clue to say that K0 is not going to be used by a certain gate at least. Alright, so I'm going to answer this question without using Logisim. Now use the poke tool to click the wire connecting to the tunnel labeled Q, so we know it's coming out of the exclusive OR. What is the second number to the right of the slash? So don't read it as one thing. Basically, what is the second number? Which is kind of the one on the right hand side of the slash. So the parentheses to the right of the slash is basically referring to the same thing, except it's using the slash as an anchor so that it's relative to the position of the slash, as opposed to what is the second number is just referring to the fact that you will be seeing two numbers, and I'm just asking what is the second one. And in this case, because most people, when they're reading English, and this is written in English, we read from left to right, so the second number is the one that is on the right hand side. Alright, so I apologize if that was not clear. Alright, so I'm going to say the answer is going to be a 0, okay, because 1 and so when you look at the bits, okay, this bit here, the least significant bit or bit 0 is going to be exclusive ORed, okay, and the exclusive OR between 0 0 is a 0 because they are the same, and then the exclusive OR between the 1 and the 1 is also going to be a 0, and then one more time for bit 2. So in this case, I just got lucky, okay, they all have exactly the same bit, so the answer is a 0. Some of you gotta get negative numbers because well, we are not going to talk about why those things are shown as a negative number. It's mostly because there are multiple ways to look at a bit pattern, and there's a signed way and there's an unsigned way, and that's why some of the bit patterns can be interpreted as a negative value. Alright, so question number 3 has the instructions to construct a new circuit of K1. And let's go ahead and do that. And there's a text. Someone got a 3 last night and it was marked as correct. How could something like that happen and be correct? Well, if the bit pattern turns out to be 0 1 1, then it is 3. Exactly. Nobody, I mean, okay, it doesn't change every single time. It changes most of the time. It does change. Okay, so it's drawing the cases from a pool. I cannot remember how big the pool is, but it's drawing from a pool. So there is a very slight chance that if somebody reattempts the quiz, they get exactly the same values to work with. But more likely than not, they're going to be different values. So some of you might get the same question, but it's all chance, it's all random. Yep, I specifically designed the activity to be like that. Whenever I get a chance, I'm going to kind of randomize things and throw it just so that you guys get a slightly different question every single time. Yes, it does take extra work on my part as well. In fact, okay, let me put it this way. From your perspective as a student, it doesn't take you any extra work, right? Because as long as people are working on their own lab or assessment or test or quiz or whatever, they don't really need to know whether everybody else is getting the same questions or not, right? So from your perspective, it doesn't really take any extra work. But from my perspective, it actually takes quite a bit of extra work to make this thing work. Mostly because the scripting language that I was using, that Canvas allows, does not understand binary numbers at all. Okay, so I have to use like some really cumbersome math to turn binary numbers to become base 10, so that the base 10 number looks like a binary number. It's just cumbersome. Yeah, for that part, I really do not like Canvas. Not at all. Alrighty, so let's move on and let's create a new circuit. So we go to Project, we say Add Circuit, and this is K1 that we're creating. And it's going to need 3 input pins. So if you're like me and you go like, but we already have things like that, right? We already got 3 input pins, and for the most part, they are correct already, and can we just kind of copy and paste? The answer is, oh yeah, we can just copy and paste. So you can even do something like this. Select these 2, control click on the 3rd one. Oh, shift click, sorry. Shift click on the 3rd one. So now I have 3 pins selected. Then you type control C to copy to the clipboard. Go to the new circuit, double click on the new circuit, and then just do a control V to paste in here. So now I have all the pins that I need already, even though the heading is wrong for the first 2. That's easy to fix, right? I mean, oh wait, never mind. These are tunnels. Tunnels do not work across circuits. Alright, I gotta play this one. Yeah, I just booed myself. Yep, I deserve that. I deserved that. Yes. All right, there we go. Okay, so now we just have to change these guys. The first one is going to be uppercase P. I mean, which one is P, which one is G? You know, you just have to be consistent. I think it's a good idea to follow what the question is suggesting. Yeah, I think I look like that a lot of times. You know, it's called the resting bitch face. Yeah, yeah. I go to certain events and other people say, "Tech, what? How come you're not smiling? You know, just smile and be happy." And I wasn't really actually upset, you know, but someone, you know, just thought that I was upset for some reason. So that's called the resting bitch face. All right, so this is going to be our output, which I'm going to call K1. All right, so now what do we do? Well, let's go back to the question and find out what it's asking, right? So the question says, now that you have all the bits needed to compute the carry bits, let's start with a new circuit K1, okay. To make the main circuit simple and clean, use multi-bit input pins P and G in the K1 subcircuit. So this is all I have done so far. Then use, okay, that's bad grammar there. Then use splitters to split P and G to the bits that you need to compute K1. Alright, so I gotta say this, okay? You know, I saw at least one person with a circuit that connects P and G directly to the gates. It's like, you might want to read the instructions a little bit more carefully. I know the grammar is wrong. I apologize for the bad grammar. However, it does mention the word splitter and also the verb split, okay? So just by reading the instructions a little bit more carefully, you know, certain people in this class would realize, oh, okay, so that's how we get to the individual bits that we need for the computation. All right. Yeah, but except it really should not. Except it really should not, okay? Because, you know, it's that's how we get to the individual bits. Okay, so the second thing, okay, because somebody mentioned your subscripts earlier. So what do we do now? Well, what we do now is we refer back to the notes and find out, you know, how K1 is expressed. All right, so we can see how K1 is expressed down here, down a little bit. There we go. So this is how we get to K1. Your K1 is expressed as G0 plus P0 K0. Okay. First question is, are we really just adding, or is that a disjunction? Right? Because that's really the first question. Which one is it? Are we adding? Is it arithmetics that we are doing here, or are these logical operations? They are logical operations. Very good. Okay, so if these are logical operations, that implies G0 is one single bit, P0 is a single bit, and K0 is also a single bit. And what is the convention that we used in this class? What is P subscript I? What does that mean? What is the subscript I saying? We have been using this notation since the base conversion module, right? You know, D subscript 0, it is the digit, is the exactly, okay, you know, a bit is a binary digit, it is a digit, right? So the subscript is telling us which position, what is the position of the digit that we want to use, because in this case, you know, we're only using one of the many digits of P, one of the many digits of X, and one of the many digits of Y. So the subscript notation is trying to tell you which bit we want to utilize. All right, very good. So now we are gonna look at this equation here, and one thing we can do is to do something like this, because I cannot remember. Okay, even though I derived all of these things, I cannot remember exactly how each bit is defined. So I'm just gonna copy it, shift back to Logisim, and then paste it. So this way, I don't have to remember. I don't have to go, oh, that doesn't work, does it? Um, okay, so, Firefox, you are embarrassing me. Copy to clipboard. How about that? That should work, right? Let's see. Unless your Logisim doesn't really care about the clipboard of the no, it does not. This is actually funny. All right, fine. I don't have a choice but to actually have to hand enter everything. That is that's just lame. All right, there we go. Fine. Screen clipping. All right, so what we're going to do next is to implement this using logic gates, right? So when you're using logic gates to do something like this, you kind of need to know, which gate, the output of which gate becomes the input of which gate. So I'm going to add an extra pair of parentheses, which really should not be needed because we have already defined the priority of operators. So we're performing the AND first, and then we perform the OR. So what that is telling you is the output of the AND gate becomes one of the inputs of the OR gate, because the OR is the last operation. It is closest to the output of the circuit, and then the AND is actually further away from the output because it has to be done first. The result of the conjunction is used by the OR gate. That is how we map expressions like this to the structure of the gates. So knowing that, we are gonna drop a few things into the picture, and then we'll do some connections. So the first thing I'm going to do is we know we need splitters, right? So, because that's actually part of the instruction of this particular step. So we're going to drop a splitter, and we're going to make it so that it has the same number of bits at least. And if you really don't want to mess around with, oh, now I have to specify which bit goes to which splitter, just configure it so that the fan out is exactly the same as the bit width. It is okay to leave some of the split end not connected to anything, but this way you don't have to do any extra work. Be like me. Just be lazy. Just get just say I'm gonna do the minimum possible to get this done. Alright, next we need some gates, right? So we get to gates. We need an AND gate, and that's the first operation. I'm going to place it here, more or less. And then we have an OR gate that is the second operation, so that's going to be very close to the output pin like that. Alright, so now that we get all of these things into a bin, okay, this is how my previous employer create new products. They just throw a bunch of chips into a pan and just kind of shake it a little bit and go like, yep, this is a new product now. I mean, not literally like that, but conceptually it is like that. Alright, so there are certain things we can just wire up right away. The output of the OR gate becomes the output. Yep, that's fine. And you might notice that this gives us an error right away, right? The reason why it's giving us an error is because the inputs are not connected to anything. So when you're trying to say, oh, this is the result of an OR, but you're not telling me what you're ORing, I'm just going to say error, right? You're going to say Robinson, error, Robinson. Does that make sense? When the input of a gate is not specified, the output is just going to be like, I have no idea what the output is supposed to be because you're not giving me enough information to do the processing. Yes, very good. Alright, so what do we do next? Well, we have the OR, and one of the things goes straight to the OR gate, and that's going to be G0. So we're going to hook up G to one of the splitters, P going to be going to one of the splitters, and G0, which is this one here. Now, how do I know that is G0? This is G, and the split end says this is bit 0 of G. That makes it G0. So G0 is going to go to one of the pins. It doesn't matter which one you connect to, as long as it's one of the pins, we get. Exactly, Chris. All right, so we got one half of the disjunction done, but the other half is it uses the result of P0 and K0. K0 is the easy one because it is right here. It's just the input pin, and then we need to get to P0. This is P, goes to a splitter, and this particular split end up here is 0. So we just hook that up. I know this. I know I could have rearranged things so that this picture looks a little nicer, but functionally speaking, hey, this is fine, not a problem. All right, so now we're gonna hook it up. Okay, that doesn't look nice. At least line up a little bit here. There we go. All right, so we are good now. All right, so I'm looking at the text channel, and then when we poke the far right 0 on G, it'll turn on G sub 0. That is correct, because when we write numbers, the right hand side is the least significant digit, which is digit 0. So that is corresponding to digit 0. Yep, that is correct below. Alright, so we got K1 done, and we want to look at the appearance and hope nobody just kind of move the pins around, because that's going to mess up the circuit tester. Okay, so when you get to this screen and you want to create the look of what I had, there's no easy way to do it. Okay, it's just P, G, K0, and then K1. This is how I do it. If you guys have a better way to do this, you are a better there's a name for people who do this sort of work. It's a circuit technician, maybe, but it's a technician position in the company who actually do all the drawing. And then you might be asking, so if it's a technician who's doing this kind of thing, then what are the engineers doing? Well, the engineers are the ones who would draw a circuit on a piece of napkin using ketchup, and then give the technician that napkin with ketchup and say, okay, I want this to look nice in whatever layout tool the company is supposed to be using. So that is traditionally how they divide up the responsibilities. So the engineers are the ones who come up with the design, and then the technicians are the ones who capture the design using a tool so that it can be used for manufacturing. Yep. Well, I'm not going to say anything about Intel or working at Intel. I have never worked at Intel, and that's why I'm still here. I'll just put it that way. Alright, so we got this part done, and then they ask how many AND gates are needed in the circuit K1 to compute K1. So it is very specific. It only asks about the circuit of K1, which assumes that your inputs are P, G, and K0 already. So all the AND gates, in order to compute the G bits from X and Y, they are not included in this count. So this count should be just 1 right there. I didn't use splitters. Mine was messed up because I set my gates to 3 bits. Exactly. Use splitters because the calculations are supposed to be single bit calculations. They are Boolean operators. If they're Boolean operators, they're working on 1 bit at a time. So there we have it. Well, besides, the most important part of that discussion of what Jose and Bilal are talking about is when you look at this particular equation here, you can see how it's using subscripts, which means even though there are multiple K's, multiple G's, multiple P's, in this particular equation, it is addressing exactly which bit we need at which part of the Boolean expression. So that is a clue to say that, oh, we need to extract only one bit out of G, one bit out of P, and the result is just giving us one bit of the case. All right, so I think that's kind of important. I'm hoping that I'm kind of pointing out, how to read the instructions and how to kind of connect the dots, okay, so to speak. You're given a lot of dots, but you need to know how to connect the dots. Part of that is reading comprehension, and part of it is really familiarity of the notations themselves. Now, notations is not too it's not too difficult, because you can just kind of you can quote unquote study, because the way things are notated in my notes is explained, but making the connections between the dots, that can be it really takes practice and time. Okay, I think my mic is clipping, so I am just gonna change that a little bit. Just reduce the gain a little bit. Most of the time, it is going in the opposite direction. It is too soft, but today, for whatever reason, it's a little bit too. Maybe I just placed the mic differently today. All right, so now it should not be clipping as much. There we go. Slightly better. All right, so that is done. We move on to the next question. Question number 4. Now that you can create a subcircuit for K1, do the same with K2 and K3 using their carry look-ahead formulae. If your K2 and K3 circuits make use of other K of n's in K n circuits, then you're not using the carry look-ahead formulae. Okay, so because in prior semesters, some people just kind of say, oh, so this is K2, and according to, okay, let me refer to exactly which part I'm talking about. So according to this line here, the first line, K2 makes use of K1, and that just completely defeats the purpose of carry look ahead, okay? Because the whole idea is we don't want that dependency. We want, besides, if this is what I need, why would I spend the time to do the derivation to the last part, right? So, in the lab instruction, I just kind of made it very clear: don't do that. When this step is done, the Explorer pane of LogiSim should have K1, K2, and K3 as available components. Blah 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 blah. All right, so let's go ahead and do that. And then the answer is, once you have all the K values, what else do you need to compute the sum S bits? Okay, so we'll answer that question in just a little bit, because right now we are going to spend a little bit of time to finish up the LogiSim circuit. All right, so there we go, and I just need to. All right, so there we go. All right, let's see. Yeah, I cannot copy an entire circuit. Yes, I'm trying to be a little bit, let's just say that I'm trying to save some time here. Alright, that's okay. We can just go ahead and create K2 as an empty circuit, and then we'll go ahead and create K3 also as an empty circuit. So now I go back to K1, and I'm going to do a copy, paste, and modify. So just go ahead and select everything. Now, actually, I might as well just select, including the label here. Okay, so copy, Control C, copies the circuit. Go to the K2 circuit, Control V, paste it here, and then double click on the K3 circuit, and also Control V to paste it over there. So now I have 3 circuits, and they are all the same as the K1 subcircuit. So now we need to make some changes. The first thing I'm going to change is to change the name of the output pin, so that K2 outputs K2, and then K3 outputs K3. Now, obviously, the labels are really only for your, so that you can actually, when you look at the circuit, you know which one you're dealing with. Other than that, no one actually gets to see how you label the output pins. Alright, so most of the components here can also be removed, so especially the wires. So I'm just using shift click here to select all the wires that I want to get rid of. Now, some of these probably can just stay for a little bit longer, but I'm just gonna remove all of them. All right, and this is for K2. So we want to look at the K2 equation, which is down here. So K2 is going to need two AND gates, because one AND gate to deal with P1, P0, K0, and another AND gate to deal with P1, G0. One is 2 input and one is 3 input. All right, so we're going to go back here, and I'm just going to duplicate this one and then specify that it has 3 inputs. All right, now we can go back and find out, how are we. Oh, the OR gate is also going to be a 3 input OR gate, because we have 2 inputs, coming from the outputs of the AND gates and one that is coming straight out of one of the G bits. So this one is going to be a 3 input OR gate. And then these wires can go away. There we go. Alright, just because of the positioning of K0, I probably want to place the AND gate that makes use of K0 at the bottom. And this is extra. So let's see. Let's check out which one is making use of K0. So it's the 3 input AND gate that makes use of K0. So I'm going to place that one at the bottom. So this one is at the bottom. This one is going to be on top. And we know that K0 is one of the inputs of the 3 input AND gate, like so. And then the other two are P0, P1. This is P, this is 0, so P0 is right here. And so unless you're kind of fuzzy about, I want my circuit to look really nice, well, I mean, it's not too bad to. I mean, this one is not too bad. The other one, K3, gets a little bit more busy. And the output of this AND gate is going to go into one of the input of the OR gates. All right, so there's a question. Prof Tech, you don't use 3 OR gates because you do your operations from left to right, and we have 3 OR gates with 2 inputs in each. Well, this is I remember this is also something that we kind of talk about in class, is when you have something that looks like this, you basically say that the last operation is a OR operation. It just has 3 things to OR. So we have G0 as one component, P1 G0 as one component, and then P1 P0 K0 as one component. So you basically use one single OR, but it has 3 inputs. So you're ORing 3 things at the same time. So it's one gate, but it has 3 inputs. Alrighty. So the second one is P1G0. So, alright. So we're going to take P1, which is already extracted here. So P1 already has a has a wire. So we'll just go ahead and connect that. And then G0 is coming from here, and it goes straight to here. And some of you may say, wow, Tech, that actually looks kind of nice. Did you plan this? The answer is nope, I did not plan this. Not even the slightest. All right, what is the third one? The third one is G1 all by itself. Okay, so G1, which is this Y here, does not go into one of the AND gates. It just goes straight to the OR gate. So you just go here. Yeah, it does line up pretty good, doesn't it? There we go. All right, so now we have the K2 circuit, and obviously the text is wrong. I'm just going to delete it. There we go. And now we're going to work on the K3 circuit. But before we do that, let's go to the appearance. And for those of you who like to document, I believe you can probably just kind of pick out the labels from earlier and then paste it here. But you have to be super careful when you do that. Let me just try that, okay? Because when I say something, I go like, well, maybe I should try it first. Yep, let me try it first. So you have to be careful because you don't want to accidentally move the position of the pins. So you want to go to the selection tool, the pointing tool, And just be very careful and do a shift click. Just hold down the shift button all the time, and then just click on the item that you want to select, like that. Like that. Okay, there we go. Okay, so now we can do a Control C to copy, and then we go to K2, go to the appearance mode of that, and then Control V to paste. Aha! So voila, it does work. Okay, cool. Except K1 is wrong because now we are working with the circuit of K2. So this time, I just change to the text tool and then click on the label, and it does allow you to change a label, the value of a label. So there we go. And now we are moving on to K3. So once again, we're going to delete all the wires. Now with this one, it would actually make more sense to make a copy and paste from K2 because it's going to be more similar to K2 than K1. So let me do just that. Okay, so get rid of all this stuff and then copy and paste from K2. Alright, so copy, Control C, and then go to K3, paste, just like that. And once again, we want to remove all the wires because between the carry bits, they do not, the way we hook up the wires, there's very little similarity between the subcircuits. Alright, so my watch is buzzing. It's time to take roll. So let's do that first, and then we'll be back here. So this is also a very short break, so that you guys can rest a little bit. Alright, so right click, open a new tab, and then we go to the activity down here somewhere. There we go. And I'm going to move it back up to kind of where we are at, and then unhide it. And I just chose a new word to, that's like an hour ago, or so, and I cannot remember what word I have chosen. Alright, so the word that I had chosen was quickly. Quickly because the whole idea of a carry look ahead adder is to perform the operation quickly compared to a carry ripple adder. So that's why I chose this specific word. So go ahead and copy and paste the word quickly from Discord into the question, and that's how and then you're done with roll taking for today. And as you guys are doing that, I am switching back to here and also going to my notes here to look up what is K3. Well, I mean, you got about 10 minutes of kind of of time, so even if you have to walk away for a few minutes, it's not a big deal. Well, that reminds me, I have to finish my coffee. I'm not going to comment on that. I can finish, showering in 10 minutes. Coffee at 6 p.m. Yeah, well, my brain is, so insensitive to caffeine. It doesn't really matter all that much. It's actually the bitterness of black coffee that kind of keeps me awake. It's like, ugh. Okay, I'm good. Alright, so K3 is like this, right? So we need one more AND gate, and then the OR gate needs one more input. So you can probably see the pattern now, right? You can, if you look at the way I do this, and you're starting to say, there's a pattern to this thing. I mean, there seems to be a specific pattern of how things are wired up, what we are deleting and what we are adding to the circuit. That's good, okay? Because noticing pattern is a very important task when you're programming. Because programming, after all, is really just capturing the pattern of how something is done. It is also called abstraction, right? So abstraction is a very important skill in just about anything related to computer science. Any job that is worth the pay, is going to involve some kind of abstraction and some kind of logical thinking in the field of computer science. All right, so we are now going to change the design just a little bit. Okay, so the OR gate needs one more input, so now it has 4 inputs. And then with the gates, we know that there's one gate that now has 4 inputs, so I'm just duplicating the one that already has 3 inputs and change that to 4 inputs. And now we just have to figure out how to wire up the whole thing. So which one do you think we need at the bottom? Which one actually makes use of K0? I mean, you probably noticed that pattern just from how I worked on K2. So which one requires K0? Which of the AND gates, right? The 2 input, the 3 input, or the 4 input? Yep, the biggest one, the one that has 4 inputs. So that becomes a pattern, right? You just started to notice the pattern of all of the AND gates. The one that has the one that has the most number of inputs is the one that makes use of K0. All right, so let's go ahead and wire up K0, and this time I need to kind of leave some space, so that I got space to work on the other gates. So I'm gonna place it a little bit differently this time. This goes to this one, and then when you go back and look at the actual formula, oh, okay, this is the same thing. This is exactly where I need it to be. So you can see the one AND gate that makes use of K0. It's also the one that doesn't care about the G bits. Okay, it just uses a bunch of P bits. In this case, it uses P0, P1, and P2. So that's if you have started to notice these things, that's a good sign. Okay, because you're starting to say, oh, so maybe there's a way to generalize the way we structure this kind of circuit, and that will eventually lead us to the expression that someone commented on the other day, the one that has all the big AND and the big OR operators. So I'm going to explain those in just a little bit. All right, so okay, my bad here. I did not release the mouse button and accidentally connected these 2 terminals of the AND gate. All right, so next one is the 3 input AND gate. So let's take a look at what that one needs. It's G0, P1, P2. So you can see the pattern, right? The previous one has G0, P1. This one has G0, P1, P2. You can probably guess the next one for K4 is going to have a component of G0, P1, P2, P3, right? So that's something that you probably is starting to notice. It's like, oh, there's a pattern to these things, and certainly there is. All right, so we need G0. Okay, so here's G0, and do I want to make things line up a little bit better? Nah, probably not. And in fact, what I want to do is to move this one down a little bit so we get more space later on. All right, so we need P1, P2, and G0. But I'm going to wire this thing up just so that when you read it from top to bottom, it will follow the same order as displayed in the equations. So this way it's not going to be like, oh, just randomly, assigning the input bits to the gates. Okay, there we go. All right, so the one that has 2 inputs, for the AND gate, that one has G1, P2. So we have G1, which is here, and then P2, which is here. So this one just accidentally lined up to here, and then the G1 is coming from here, and we need a little bit of, oh, that's not going to work. That is not going to work unless I move this a little bit to this side, because I kind of need that space for that right angle, for the right angle of this wire. So now we can hook that up. Whew, okay. Not too bad. And now we can look at this and go like, hey, G2 is not connected to anything. All the inputs of the AND gates are occupied. What are we going to do with G2? G2 goes to one of the inputs of the OR gate. It is not ANDed with anything. Okay, it is just used by the OR gate, but not of the AND gates. Alright, so let's see. How am I going to wire this up? Well, there's a way for me to wire this up so that it actually looks nice, but I'm debating whether to do it that way or whether just to kind of put this one to the first one. And to do that, I'm going to have to move the entire circuit down a little bit. So select everything and just grab any part of it to drag it down a little bit like that. Alright, so this is what I'm going to do. I'm just going to bring this all the way up to the first, the top input pin. And you have to be careful and make sure that you make a connection to the actual port of the part, because if you just visually connect it to something in the display of a gate, it does not it doesn't mean that you actually have a logical connection to one of the ports of the gate. So you got to make sure that when you release your mouse button, the cursor looks like a bubble. Like, oh, it doesn't actually do that. Oh, that's because, oh, this is a very good example, because I actually did not connect it to a pin. Okay, let me do it one more time. Let me just make that mistake one more time so that you can see what I mean by that. See this? It's not actually connected. On the other hand, if I just get it down here, it still doesn't show it, but this time it is connected. I think the first time it was connected to. But you can always confirm the pins of a part just by hovering a mouse pointer over first. So now you can actually see this is the connection point, or this is the port. And so when you drop or when you finish your wiring, you can actually make sure that you end up there. That is funny. Well, by the time we get to the von Neumann architecture, I'm going to show you how older computers were quote unquote programmed. It's actually worse than that. It's actually worse than that. Yep. And I think this is why we like wireless technology, right? All right. So K3 is now done. Change the output pin so it reads K3, like so, and also change the appearance. So we go back to the K2 appearance, and very, very carefully, pick out the things that we want to copy and paste. So keep the shift key down and then select, click on the items that you want to copy. Yeah, you have to be very careful, because if you accidentally move a pin, then the test circuit, the circuit tester is not going to work. So now we type Control C, switch to the K3 circuit, switch to appearance mode, and then just paste, and then we get everything down. Except one of them needs to be changed. K2 is no longer right. It should be K3 now. There we go. All right, so let's switch back to the quiz and see what we are asked here. Oh, there we go. So once we have the K values, what do we need? What else do we need in order to compute the sum? The P? Nope. The P's are only needed for the K circuits to work. The G's are the same thing, so it is actually the Q bits that we need in order to compute the sum, because the S bits are the R of the Q and the K bits, and that's why the answer is the Q intermediate sums. All right, so we are basically done, because the last one here is more like instructions. It doesn't actually have any points. So if you get to the circuit that I have here, where main doesn't actually do anything with K1, K2, and K3, but it's ready for testing, okay? And that's because the circuit tester is specifically pulling your K1, K2, and K3 circuit into the test circuit itself. Okay, so the next step I'm going to do is to show you guys how to make use of the circuit tester, because I think it is important to understand how to use a circuit tester. So this way you can actually test it first. Okay, if it doesn't work, don't turn it in. Fix it first and then turn it in. So I'm going to do exactly that. Okay, this step is entirely optional. Blah blah blah. Okay, so to download a file, okay, this works on my computer. I'm not really sure, how your computer is configured or what you need to do to your browser to make this work. Okay, I'm using Firefox, by the way. So you right-click on the link, and then you go to Save Link As. Okay, so this is all I need to do, and then it prompts me, to okay, where do I want to save the file, right? And you cannot see the top portion, and I cannot really move this window, but you kind of get the idea, right? In fact, I can probably move the entire thing. Nope, doesn't work that way. All right, and I don't think this window can be moved. Oh, it can be. Okay, cool. All right, so here we can control where we're gonna download the circuit, and the default that I use is the temp folder. So I just click save, and that was just save the file. I mean, it's just a regular text file. Name a file name, this already exists. Okay, fine, go ahead and replace it. All right, so the instructions to do this, there are two versions. The easier version is simply to change the file that you have created, and copy that file to the name of 3x3ca .circ. Okay, so I haven't really saved my file yet, so let me go ahead and do that. So file, save, and you can save the file to anywhere you want. I mean, I'm just going to save it to, oh, let's see, where's this folder? Yeah, that's going to be okay. All right, so I'm going to save my file as tags part1.circ. The instruction says you can save it under any name except you don't want the name to include any punctuation or space. Other than that, you can save it under any name. So I'm just going to call my text part1 and then click save. All right. So now the question is, how is the circuit tester going to work when our circuit here is not completed? Okay, because all we did was to create K1, K2, and K3, but we actually did not finish the entire design, which is what we are going to do today in today's lab. And that automatically answers the question of, so Tech, do we have any lab tonight? Yes, we have a lab tonight, and it's a continuation of the one on Tuesday. All right, so I think it helps to open up the circuit tester just so that you can take a look at that circuit tester before you run the test. So I'm gonna open, and it's gonna be in my temp folder. So go all the way to the temp folder, and the name is test driver something. There we go, test driver 3x3ca, and we double click it, open it. All right, so there we go. So this circuit basically, makes use of a the surrounding circuit is not important. Okay, it just has a lot of test cases. That's all. The part where you might want to know, because if it doesn't work out, you probably want to know why it's not working out, is it's calling for K1, K2, and K3. And in this case, the circuit does include K1, K2, and K3, because 3x3ca is is probably a file that it can find, because I uploaded this, right? So the path to the right 3x3ca, the actual solution file, is sitting at the same place where I left it. So that's why it made the connection. So when you need to test your circuit, you need to name your circuit exactly the same as 3x3ca, and put everything into one folder. Okay, if you want the convenience, it doesn't have to be like that, but if you put everything into one folder, it works better. You just don't have to type in super long file paths. So are there any questions about how the circuit tester is constructed? It is only making use of K1, K2, and K3, and I think it tests all the possible cases. And that's how this particular circuit is used for testing what you're turning in. All right, so if there are no, oh, okay, somebody's typing a question. I will keep an eye out for that question. Does it matter if we connect G2 bit to OR gate top bit? the position is not important. So if you look at K2, wait. Okay, so G2, okay, that has to be K3 because K2 does not need that. So the positioning of which wire connects to which pin over here is not important. So the question, okay, so when I say okay, it doesn't matter, what I want you guys to do is to eventually have the habit of asking why. Okay, why doesn't it matter? What is the reason why it doesn't matter? Okay. In other words, if I want the circuit to look really ugly, this can go to this one over here, this can go all the way over here, and this one can go down all the way to the bottom, and so on. Okay, as long as each one, okay, 1, 2, 3, and 4, as long as each one is connected to a distinct port, input port of this OR gate, the whole circuit is still going to work. So the question is why? Does anyone want to give it a shot as to why that is the case? Close. It is not because it is associative. It is because it is associative. Means if you use a cascade structure of OR gates, each one only has 2 inputs, then the ordering of those OR gates do not matter. That's associative. So which algebra rule are we using here? I mean, that rule exists in just normal algebra as well, but it's not associative. Commutative, that's right. So Eric is correct, because disjunction, just like addition, is commutative. Commutative. Okay, my pronunciation is probably bad. Because it is parallel electrical connection. Not, I wouldn't call it that. I would just refer to it as because disjunction is commutative, which means the ordering of operands do not matter with an OR gate. All right, so that is important. Okay, you might think that I'm just kidding you and just say that okay, if I give you an answer, you probably want to ask why, at least in your mind. But I wasn't actually kidding, because this is how you strengthen your reasoning skills, is to keep asking these questions of why, but you're not asking it out loud because you're trying to answer the questions yourself. Now, I know during a class it is difficult to kind of get distracted by these tiny little Y's everywhere. So you might want to jot down, okay, this is what text said, and then just use a little pointer thing, point to whatever that equation is, and then just put in Y and then put a question mark. And then later on, when you're reviewing your notes, this is how you use the 5 hours outside of class time, is going through the notes and go like, okay, I kind of jot down a little question here. Let me see if I can answer that question. So that is something that is not only useful in this class, but it's going to be useful in all of your STEM classes at least. Okay, because it involves the same kind of skill set to be successful in all of your STEM classes. Alright, so we are basically done with this circuit. So let me make sure that it is saved. Control S, it's saved. And all the files are located at some random location. So my command line thing is going to look pretty ugly. But that's okay, because it's also useful for the purpose of illustrating how to use the command line. So let me move one of my command lines into view, like so. And I don't want to do this because I need to change the font size first. Because if I don't change the font size first, it's not going to work. All right, so I typically like to work on things in the temp folder, especially for things that I really don't need to save. Alright, so the full command is java-jar, and then I have to find the path to my jar file. So this is where my logitsim310.jar is located. Then you specify the circ, the test driver circuit, and the location of that. Well, fortunately, that file was saved in the temp folder, so I don't need to specify the full path because it is in the current working directory. So test driver blah blah blah, and then I need to specify which circuit I'm testing. So I need to specify and that one is changed. Okay, the reference to the component is changed. So now I need to specify sub. I think it's a single sub, or I can change the name of the file. So I'm going to use the first one, where I use substitution. So dash sub 3x3ca.circ. So this is basically specifying, oh, if the main circuit of the test driver is referring to this circuit here, don't try to open 3x3ca. Instead, open that file instead. So now I need to specify where the other file is located, the one that I just saved earlier. And that one is in 1223 and tax part 1. There we go. All right. And if you just do this, it's still going to open up the GUI version of Logisim, which is not what I want to do. So instead of doing that, I would specify dash table. Oh, excuse me, the other way, dash TTY. Basically it means, okay, don't give me the GUI interface. Instead, just automatically run this circuit until it's done, and then generate an output in what we call the standard output. I mean, you guys know what the standard output, right? I mean, that's just basically whatever C out is outputting to. So dash TTY is just saying, okay, use standard output to capture the output of running the circuit. So dash TTY, and then table, I think is the only option of dash TTY. And if you press the enter key right now, it's just going to do something like this, okay? Unless you are very quick, at looking at these bit patterns and do a match, it's better to capture it to a file. So you have a greater than, which is called the redirect, symbol, and then we redirect it to, I typically just say test.log or something like that. The file name is not important; it's just a regular text file. So there we go. We capture everything in test.log. And then the instruction here also has the reference, right? The actual correct output. So the correct output is logged here. So I'm going to use the same technique. Right click and then do a save link as. You cannot see it because it's outside of the screen area now, but it's basically the same idea. You save it to a file. And where you want to save it to is up to you, but I would just save it into the temp folder too, just so that all the files are in the same folder, just a whole lot easier to refer to those things. So you click save, and now we go back to the command line. So there are two ways to do this, okay? Once you have two text files and you want to find out whether they are the same or not. If you're using Linux or if you're using Mac OS X, any type of Unix type of operating system, diff, D-I-F-F, is usually a program that's pre-installed, and it's pretty handy because not only does it tell you whether they are the same or not, it will even tell you, where they are different. So you can say diff test.log and then test driver.log. And if it doesn't give you any output, it means the two files are indeed the same. On the other hand, if you're using Windows, then you have a program called comp, C-O-M-P, which also compares the content of two files. Now, I don't use Windows, so I cannot really tell you how that works or what the output is supposed to be, but I can just tell you that, yep, you can use that particular program. Now, since all of you know that I like to use VI, Vim, in Vim, it's actually pretty cool as well. Okay, I use nvim, which is new Vim, and it has a diff mode. So you can say dash diff, which turn it into diff mode, and then you just give it the files that you want it to compare, and it would give you, oh, okay, I think it's dash d or dash diff. I'm gonna specify dash d here. There we go. So it basically says the files are identical, because if they were different, it would have been highlighted in the output, and it would have shown me which lines were different or different between the two files. the fact that it gives me something like this basically tells me that the two files are indeed the same. So there are many ways to compare text files and quickly locate how they are different. And that's it. I mean, I'm going to upload the file to the text channel now, because that's going to be the starting point of tonight's lab. So I'm going to upload the file that I just created, and obviously I forgot where I put it already. I think it's in my home folder, Documents, CISP310, 1223, tax part1.circ. Yep, there we go. All right, so now you have a starting point of tonight's lab, because that's the assumption. Okay, the assumption of tonight's lab is you got the lab on Tuesday done to the point of where I ended up today. So now we're going to work on part 2. So part 2, I have not opened it up yet. I'm going to do it right now. Alright, so I'm confused about the second and third circ you wrote. Can you explain that again? Yes, I can do that after I release the lab of tonight. So those two circuits are basically the circuit version of the two formulae for computing K2 and K3. But the process of creating those two circuits are basically identical to the first one. Alright, so this is for part 2. And let's take a look. It's due tonight at 9:50 as usual. And as a result, let me see what I need to do here. Allow multiple attempts. Let students see the correct answer. Yep, you can certainly see the correct answer after the due date of this lab. So that's going to be tonight at 9:50 p.m. There we go. And I'm going to copy and paste this. So copy and paste this as our. Alright, so this is your passcode, is 3x3b. The letters are all in lowercase. I will repeat it in the text channel. So it's 3x3b is the access code. Save and publish. Now this one also requires you to turn in the final version of the circuit. So there is a companion activity as homework for you to turn it in, just like the first part of the lab has its own companion assignment. So this one has, let's see, right here. So this is the file submission thing, and let me just do the indentation. Just visually it is easier to see it this way. And it's going to have the same due date, because you're going to walk through basically the same thing as specified in the quiz itself. So by the time you're done with the quiz part, you would have the circuit done already, and that is why it is due at the same time. Alright, so there we go. Save and publish. So now you guys can get started. I will try to answer the question about the second and the third circuit that I created. So if you think you don't have any questions anymore, you can either mute your YouTube so that you can just kind of keep an eye on it in case you see something interesting. You go like, oh, I want to know what he's talking about. Or you can just get out. I mean, you can just disconnect from the live stream if you want to and just kind of focus on the lab. For those of you who still have questions about the second and the third circuit that I created today, I'm just going to be try to answer those questions interactively, because it's a whole lot easier when we do it like that. In fact, because I don't think there will be more than 50 people interested in how I am going to explain the second and the third circuit, I think I'm going to stop the live stream. Well, okay, I can keep that one going, so it's recorded, but I can also enable screen share on Discord, because that has a much shorter turnaround time. It's a whole lot easier for people to ask questions. So that's what I'm going to do. All right, so in the Discord server, I am connecting to the voice channel, the general voice channel, and I'm also turning on the screen share on Discord. So if you want to kind of continue this discussion because you got questions about the second and the third circuit, go ahead and connect to the Discord voice channel. If you say that if you already got everything, you have what you need to get started with the lab, you can just go ahead and disconnect everything, start on the lab, and get it done. All right. So so at this point, only people who want to continue to listen to how the second and the third circuit is done, you can stay on the Discord voice channel. And I see a bunch of people are here already, so that's good. And the rest of you, you can just go ahead and disconnect and just get started with the lab. All right. So I am going to go back to the design. And you can post the questions now in the text channel so that I can try to address those questions. Oh, that's not what I want. Oh, yeah, that's 1, 2, 2, 3, and then text first. Part 1. There we go. All right, so go ahead, fire away with all your questions regarding the second and the third circuit. Basically it's K2 and K3. Now keep in mind that I'm not gonna delay tonight's due date, so it's still gonna be 9:50, which is basically a combination of 2 lab sessions, but that's a lot of time. All right, so there's a question about the splitter. Okay, so let's go to the K1 circuit. All right, so what is the question? Yeah, that's my cat in the background, wanting to go outside. Yes, you can send a picture, of, where the question is, but I cannot answer questions about your individual design because right now I'm trying to address questions for the one that I did today. Alrighty. So the law said he had questions about the second and the third circuit, which is K2 and K3. So go ahead and ask the questions now. You can use the voice channel as well if you want to. Redo the lines. I'm not sure what that means, Taylor. What do you mean by redo the lines? Alright, so I thought my bits matched up, but it's blue in that section. Alright, so let me take a quick look here. Well, if they are blue, you might want to just kind of restart the simulation because that might be the reason why they are blue. Is somehow your simulation is either disabled or Logisim has bugs. Okay, so if it shows something like that, you can save your file, exit Logisim entirely, and then come back in. And if the problem persists, then you want to check, to make sure that simulation enabled has a check mark here so that it is actually simulating. So that could be the reason. All right, so that's good. That fixes one problem. Any other questions about K2 and K3? Okay, I'm not seeing any. Oh, okay, so Jose is typing. So the rest of you who are watching this on the Discord server, if you have any questions, go ahead and ask those questions because I'm not, there's nothing for me to volunteer at this point. I'm just responding to questions. Okay, so it's making sense. All right, and you have the file now. I mean, you guys have all have the file that I just worked on. So maybe not right now because right now your task is to finish up the actual adder. But the five and the third of an hour for this week, maybe you can use some of that time to really examine the way I did um, this part of the assignment, and note anything that you did not know previously, and just kind of just write the note and not just really go like, oh, okay, that's interesting, I did not know it. No, if you are thinking something like that, write or type it, okay? Because the process of writing, the process of typing exercises a different portion of your brain, and as a result, when you're reasoning, because the worst part is when you're trying to do reasoning, if you don't have any retention of the material, it's not going to help. It's just like you have a Corvette with the latest and greatest V8 engine, but you don't have tires on the car, okay? So the Corvette is not going to go anywhere. It's kind of the same thing here, okay? You gotta have the concepts down, the definitions down, the symbols down. That's your tires, okay? Then at that point, the reasoning ability, that you have developed is the engine, okay? So now you have traction. Your Corvette would actually go places. So if there are no questions, I'm probably going to disconnect from the voice channel too. So I just want to see if there are any questions that you guys want to ask before I disconnect and grab a few bites. And then in 10 minutes, I'm going to come back and start to answer questions in the text channel. Okay, so I gotta use this little thing here. Yeah, there we go. Okay. All right, so it looks like we do not need to continue with the Discord session, so I'm gonna sign off right now, grab something to eat for dinner, and then I'll be back to answer questions. 5 minutes tops. Okay, so I'll be back.